Okay, maybe we should start. So, Professor Nakamura, it's our great honor to have you as speaker this evening here at our meeting. And it's also my pleasure to introduce you to the audience. Some of you are, of course, well familiar with the work of Professor Nakamura, but in any case, let me tell a bit about him. So he started his studies in Japan at the University of Tohoku, and then went in the US for his PhD, which he got in '63 at Penn State University. And then most of his career, Professor Nakamura spent in Texas, eventually coming to the University of Texas, where he also became professor. Today he's Professor Emeritus of the Institute of Geophysics of the University of Texas. And he was among the pioneering researchers that looked at the seismic data of the Apollo program. And not only did he produce a wealth of scientifically important analyses of the data, but also made sure that everybody else who was interested in the data would get a start and help from him to understand the data, because that's not really trivial if you don't know what you're looking at. And that was also how I personally got in contact with him in 2010, when I wanted to look at the Apollo data and I didn't understand what it was. And he explained it in all detail to me with event catalogs and whatever he wanted. He was the source. So, and I think still today, even though many people have studied the lunar data, is still the most important expert in the world when it comes to Apollo seismic data. And so, yes, Professor Nakamura, I leave the stage to you, and I will actually be the person who will change slides for you. So you just let me know when I have to go to the next slide. Thank you very much.
Okay, thanks. Well, good evening, ladies and gentlemen. It's a great honor to give this talk, and I really thank you for staying late to listen to this talk. And I'll try to make it short enough that you have any other activities you want to interfere with those activities. Anyway, what I'm talking about is, may I have the next slide, please? Can we go to the next slide? Oops. Yes, well, right. Well, what I'm talking about today is an old story. It's half century old story. And I know many of the audience here are not even born that time. So, but anyway, there's still things important about what we did then. So I'll talk about those and understand that Taichi Kawamura has already talked about many of the things I was going to talk about. So maybe I shouldn't talk about those. But anyway, I'll just briefly mention what we did, just to make it complete that what we did earlier. And also I need to warn some of those people who attended last workshop. It was 2.5 years ago. And since then, not much I haven't done that much since then. So it's essentially the same as what I said earlier. So I apologize for giving the same kind of talk twice. But anyway, some young people who are not there might be interested in what happened a long time ago. And also, so anyway, the main purpose of this presentation is to tell you about what happened long time ago, 50 some years ago. And first I talk about what kind of seismic experiment was done that time and some related experiment. And and what sort of instrument we had that time, and what we recorded and what we found out with those data. And then I'll talk about what happened to those data. And are those data still available? Yes, they are in a different ways. And what kind of data we have. And the interesting thing about those data, those all data still contain many information which are still waiting to be extracted as a new way of analyzing the data, processing data become available. And I won't be surprised that those data are still, your young people are finding something entirely new from those data. And then we shortly talk about the future plan, but I think other people have already talked about that, so I can probably skip that. And then leave enough time for questions and answers if you have any. We have next slide, please. Okay. Sorry. As you all already heard that there are 1, 2, 3, 4, 5, 6 sites where the Apollo was landed, and 13 was skipped because Apollo 13 was unable to go to the moon, and the astronaut did return to the Earth, but the instrument was still going around the sun. But anyway, those 6 instruments, except 11, they worked very well, and until the end of the project in September of 1977, where other projects are coming up, and even some instruments are still working, including seismometers are still working. NASA had to turn them off, and this was the end of data acquisition. Apollo 11, as Taichi Kawamura talked about earlier, and because it was not covered by thermal shroud to protect from heat, daytime heating, and so it died after the second lunar day. So it worked only about 21 days or so. But anyway, the other instrument worked very well. And one thing you might notice is those instruments all located near the center of the moon, near Earth's point. It's not far from the supposed point. So its coverage is rather limited. And this is something in the future we are trying to do, is extend this coverage. But anyway, this is what we had. We have the next slide, please. Besides passive seismic experiment, which was heavily involved, there are some other seismic experiment, well, sort of related seismic experiments, and those are active seismic experiment and ASE and the LSPE, which is lunar surface profiling experiment. Those are active seismic experiment with geophones, and similar to the ones used for seismic exploration, and to find out the shallow structure of the moon. And finally, you probably heard about LSG, which is a lunar surface gravimeter. That was first attempt by Joe Weber to use the moon to detect gravitational waves. And unfortunately, this did not work as a gravimeter because of some error in in constructing the instrument, but it worked as a sort of short period seismic seismometer. And there are many other experiments listed in here, and which well, you can read that what those experiments are. But anyway, there's a type of experiment done with ALSEP. Oh, I might mention that ALSEP was deployed at station 12 through 17, and Apollo 11 was called, strictly speaking, it's not ALSEP but ESEP, which early, let's see what EASEP, early surface experiment, whatever. May I have next slide, please? Okay, this shows that kind of seismometer we had, the passive seismic experiment. On the left-hand side, it's one which contained 3-component long period seismometers. Well, we called it long period at that time because but nowadays the instruments go much longer period than what we were able to use that time. So now in the present terminology, it's a mid-period instead of long period. But anyway, we call long period, and 3-component, and then single vertical component short period seismometers. And what's shown in here is one which was supposed to go to Apollo 18 or 19, but since those 18 and 19 are canceled, so the instrument still stay on Earth without going to the moon. And actually, the one shown in here is the one sitting right in my office right now. And the one shown on the right this is same as what Aishi Nakamura showed earlier this afternoon, at how the instrument looked like on Apollo 16 stations. It's covered with thermal blanket to keep from daytime heating and nighttime cooling to keep the temperature constant. This was made after Apollo 11 instrument failed, that we have to protect this from heat, direct solar radiation. And what you see on the right behind it is what they call central station, which is with antenna and which transmit all the data directly to the Earth. And at that time, the instrument, well, there's no way to store the data on the moon. So everything was transmitted in real time to the Earth, and all 4 stations working simultaneously. The signals are received on Earth same time in real time. And this was very fortunate because at that time it was not possible to correlate signal from one station to another on Earth at very high accuracy. But this was the first time signal from different locations on the moon were recorded simultaneously with extremely high relative time accuracy. And because of this, we are able to correlate signal from one station to another, and because of by using that, we can locate source in a very high accuracy, much higher accuracy than sampling rate of the instrument. And see, actually, this happened to be the first time what they now call seismic interferometry. You can correlate signal from different stations to determine the location or time difference between signals at very, very high accuracy. And this was one thing when we go to the moon again, we need to think about it, how you can do something like this, and it may be possible. But anyway, that's one thing we learned. Also, this whole thing was powered by RTG, which is, you can see behind on the left-hand side further away, which is what they call RTG, radioisotope thermal generator, which powered this instrument. But look at next slides. This is just a rough diagram graph showing how sensitive those seismometers are. And there are 1, 2, 3, 4 lines there. The one for short period, the light blue line, the short period peaked at about 10 Hertz. Oh, I'm sorry, the two diagrams here. One is shown on the left, it's shown its displacement resolution in terms of ground displacement in meters, or digital DU. DU stands for digital unit, the smallest unit of digitization of the signal on the moon. And and one on the right, it's this graph showing the acceleration resolution, which is ground acceleration in meter per second square per digital unit. And so the short period and long period LP, well, operated in 2 different modes. One mode was, it's actually designed to operate in flat mode, which is dark blue line. And however, sometimes this instrument became unstable when the temperature went up in long period, a flat mode. So it was changed to peaked mode, which is turning off the feedback to extend the frequency range to lower frequencies. And this shows the one on magenta line, reddish line. And this was fortunate because the very high peak output ground displacement sensitivity at about half Hertz, we were able to get many long, deep moonquakes, which happened to be in that frequency range. But anyway, this is the way it was operated. And the feedback signal to make this instrument extend to lower frequency, that signal was recorded as tidal mode, which is green line here. But anyway, these are the sensitivities, and as Taichi Kawamura talked about it, this sensitivity is very high. If you operated this on the Earth, it's completely saturated the signal, and you don't see any signal at all because moon was so quiet and without any air or ocean and no activity, human activities. It's just so quiet, and we can operate this at a very, very high sensitivity. And however, if you are interested in millihertz range, which is left side here of the frequency scale, sensitivity is not very large. And, and in fact, during the mission, we did try to find any free oscillation of the moon and normal mode, but our attempt was unsuccessful. And there may be some couple of reasons. One of its sensitivity wasn't high enough. And the second reason was because if you're trying to get the normal mode, it depends on how the signals are reflected from the surface of the moon, and how the body waves are reflected from the surface of the moon. And it so happened that the surface of the moon was so heterogeneous because of impacts, and there are good reflection, coherent reflection from the surface of the moon. And that may be the reason why we did not observe any free oscillation of the moon. So if you're depending on detecting gravitational wave, you might consider this. And of course, we may be completely wrong, and there was something else there. So it's, I think, future people, young people like this, like you, need to look at this again, and probably you find what we said earlier was completely wrong. There are signals there. You may be able to find those there. And even if you may be able to find signal, even sensitivity is not large enough, but since the background noise, but the instrument response is only resolution shown in here, when the signal slightly changes, it may change level from one level to the next, and then back and another. And this may be used to get sensitivity quite a bit higher than what this diagram shows. And this is something you might think about it. And I won't be surprised that young people can look at this old data and something entirely new. But anyway, this is something. So I'm hoping that young people can get to that in some time. May I have next slide, please? Okay. Well, as I said earlier, and Taichi Kawamura told you that in our atmosphere and oceans, the surface of the moon was seismically, most of the time it's very quiet, and except sunset, sunrise, when the temperature changes, you have a small, what they call thermal moonquakes, and and you do see signals in the very high frequencies recorded at short range. And so this is thermal moonquakes. And then we recorded meteorite impacts. With that atmosphere, you have all meteorite impact, many meteorite impacts recorded. And on the long period instrument, we recorded something like 730. I have some of that number. Oops. About 1,700 meteorite impacts recorded in an 8-year period. And these are the ones recorded on long-period instrument and recorded at multiple stations, most of them. But if you're talking about the meteorite impacts occurring at short range and recorded at the short period instrument, there are many, many more of them. And then, anyway, meteorite impacts are the only natural events we expected before we went there. We thought, well, there must be some meteorite impacts recorded by instrument. So by using that, we can probably find out what the internal structure of the moon was. And it turned out to be that the meteorite impacts are not only natural events we recorded. And we recorded after we had Apollo 12, 14, we recorded many, many other type of events. And it was a big surprise that we found events which are recorded at multiple stations. And after single seismometer, we couldn't tell where they're occurring. But by two instruments, we can tell what it's occurring somewhere where, on a line, circular line, about the same some distance from those instruments, but we still couldn't tell whether. First, we assumed, well, maybe somewhere near the surface, but that was wrong. Only after we had 3 instruments, we found out those events occurring, many events occurring, actually occurring at depth of halfway to the moon. It's 900 kilometers or so. And this was a big surprise because this is deeper than any earthquakes on Earth. And those are small events, but then it turned out to be occurring every month and synchronous to the motion of the moon relative to the Earth and the sun, which means those are either triggered or caused by tides. And we're still debating whether it's just triggered by tides or tide itself is not strong enough to make those moonquakes, deep moonquakes occur. And it is actually turned out to be quite similar to what happens when you stress material with cyclic loading, what they call fatigue, stress. Anyway, I was involved before I was involved in the Lunar project. I was involved in testing aircraft parts, and when you're testing aircraft parts with constant loading, with cyclic stressing added to it, you see cracks happening when at the peak stress and at both high end and low end. And this stress is much, much lower than how usually the material cracks. So simply by applying cyclic loading, you may cause material to crack. And actually, when you are riding on an airplane, and there are many cracks occurring in aircraft parts. The thing is, as long as it doesn't crack all the way, you don't have to worry about it. And what's happening on the moon for deep moon quakes is something very similar to that. And anyway, this is very interesting finding when we went to the moon. Anyway, and the final type shallow moonquakes, those are very peculiar events, which the shallow means it's not as deep as deep moonquakes, usually less than 200 kilometers, but not at the surface at some depth, probably depth of at least 50 to 200 kilometers range. And the interesting thing in shallow moonquakes is there are very high frequencies, multiple frequencies in over 1 near 10 hours. Actually, instrument response goes down above 10 hertz, but it's probably higher frequency than that. And because interior of the moon has a very low attenuation of seismic waves, they can travel much longer distance. And there's still lots of debates of what really is causing those shallow moonquakes. And this is something we need to figure out in some future. Look at the next slides. Okay, this is just one example each of deep moonquakes and shallow moonquakes and meteor impacts. The big difference, which probably Taichi Kawamura talked about, but these are quite a bit longer. The scale here, each one is 10 minutes, so signal usually lasts for hours. Some signals last for hours, which is quite a bit different from what you have on Earth. And the one at the middle is shallow moonquakes. The top 3 traces are 3 long period signals, and the bottom is short period. And shallow moonquakes is significantly high frequency content there. And it's still a big mystery what they are. And the shallow moonquakes are shown here. We have the next slide, please. Okay, so what we found out with all those data, and one thing was using those deep moonquakes, shallow moonquakes, and also artificial impacts, which is used spacecraft intentionally dropped on the moon. We could figure out what the inside the moon was made of, and essentially, it's similar to the Earth. The inside of the moon was differentiated, making crust of something like 60 plus minus kilometers, 50, 60, and at the mantle, and was quite darkly the core. This is what we found earlier, and the mantle is top part of the mantle, lower part are quite different, and top part is high Q, which is upper mantle. It's high Q. It's very low attenuation, and lower mantle it's a low Q, which is high attenuation. And the deep moonquakes occur just above this boundary between shallow, the upper and lower mantle. And the earlier studies indicate there's some indication of having a core, but they are not good enough to tell us exactly how large those possible core was. And we have to wait until much later, last 20 years so, to look at the data again, and some studies show that there are really a core there. We have next slide, please. Okay, so what happened to the data? And when we took the data sent from the moon was just a bit strings, and the only way to record the data on what they call 7-track and 9-track reel-to-reel tapes, like the ones shown here. And at the end of the Apollo project, we had something like 12,000 tapes like this stored in our lab, and that's all we had. And this was back in late 1970s, early 80s. And however, in early 1990, the better way to record those data, digital data, became available. And it took about a year and a half, 2 years to read all the data and transfer to what they call 8mm cassette tapes, the exabyte tapes. And all those data, 12,000 tapes, data are transferred to 80 cassette tapes, 8mm cassette tapes. And then this was sent to, let's see, I look at next slide. Okay, before that, right. Yeah, this was, so those 80mm cassette tapes are archived at IRIS DMC, which is Incorporated Research Institute for Seismology Data Management Center. And so they were sent to there, and they became available from there for public. And only recently, NSSDCA, which is NASA Space Science Data whatever NSSDC, anyway, they had to go down to the Space Center. And NASA Space Science Data Coordinated Archive. Anyway, so if you're interested in those data, original data from NSSDC also. And these are 7-track tapes of data, the ones we used for passive seismic experiment, those are PSC data, and not for any other experiments. And from March of 1976 to end of the recording at September 1977, and NASA said, well, we cannot process those anymore. And so we took over processing of those data at UT in March of 1976. And all the ALSEP data, not just seismic data, but all the other experiment data, read and to and then we recorded those, and those there are also 8mm cassette tapes in 1990s, and so those are all the raw data available, and the thing is, those raw data are something which were recorded on the moon, digitized on the moon, and sent to the Earth in real time as bit strings. And bit string data, to read those bit strings, you need to know how to decode those strings of bits to any usable format. And this is maybe a big effort. So there was some effort to reformat those data, bit strings, to more usable standard seismic data format. And this has been done and recently, and those are now available from planetary PDS, planetary data systems. Let's see. The next slide, please. Okay. So if you're interested in those reformatted data, this is described in this the first reference here by Terry none others, and this was published last year in here. And so you can look at that and how they are written, and you can use those data, and that's probably the easiest way to look at the data, the seismic data. And also there's a couple of recent result, the description of how those data are reanalyzed recently, and then and how those instruments, not just the passive seismic, but active seismic and other data are made. And those reviews paper, this might be of interest if you are interested in what was done with those data. And see, I believe next one. Yeah, next one. Yes. Okay. Well, other people have already talked about this here, so this may be duplicate. But anyway, there's a new effort to extend what we did with Sapporo and get more information with a more widespread stations and do the experiment. And one of them is Lunar Geophysical Network, LGN. And only recently, a few months ago, it was considered for New Frontier 5, but it was not anymore in New Frontier 5. So now it's considered for New Frontier 6. And what sort of experiment, what sort of instrument we're going to use, those are still open to you. And so maybe you can propose what to do, what sort of experiment you want to do for detecting gravitational waves, and maybe we can include that in this effort. See, this is something I'm not directly involved, but I'm watching what those people are doing, and with hope that we'll get a good network running. Maybe not my lifetime, but in the near future. And this is a big hope. And so lots of things you can think about it. And I'm very glad that young people like you are still interested in this kind of things. And there's no limit in what you can do. And then just do it. I believe this is the last slide. Next one. Yes, that's all I can present. And if you have any questions, I'd be glad to answer those questions. Thank you very much.
Thank you very much, Yosio. Very nice presentation. So yes, I will give time to questions. Are there any for Yosio? Okay, I don't think we have more. I will run around then.
Yeah, thanks, Professor, for the nice talk. And my question is like, there are thousands of seismic activities has been recorded. Is there be any evidence for any rockfall or small meteoroids that might have occurred during the Apollo measurements?
Rock falls?
Yeah, boulder falls.
Falls?
Yeah.
That's still unknown. And as I told you, you could identify meteor impacts, and that may cause its fall, but those are not related to falls. And shallow moonquakes, there are some hypotheses that shallow moonquakes may be related to falls, but from our analysis, it does not seem to be shallow moonquakes has not very close to the surface. Well, of course, we may be wrong. There's some people said they are, but this is still an open question. So there's no clear indication that there's still active holes nearby. That's what my understanding is.
Yeah, thanks. So I have one more question, like the crustal thickness of MAHE and Highland, do they have any effect on the seismic signatures that reach the surface?
Effect on what?
Crustal thickness.
Yes.
So do they have an effect?
Crustal thickness have any effect on
the seismic signals which reach on the surface?
Or
because on highlands, there are very less number of reports. So most of them are in the MAHE patches.
Oh, okay. Well, it's hard to tell because if you're comparing station 12 to 16, there's a clear difference. Station 16 is highland, station 12 is MAHE area. And there is a significant difference. There are more signals recorded on 16 than 12. And other than that, what other sort of effect on signals? I don't know. It depends on what specific signal characteristics you're talking about. Maybe I'm not answering your question.
No, I just ask about the thickness, because in highlands we have 50 to 60 kilometers of crust, but whereas in MAHE it is 30 to 40 kilometers.
Right.
So we have seen more epicenters on the MAHE patches. So we need more instruments on highland so that we can detect any seismic signatures on highland part also.
I don't know the answer to that question.
Okay, thanks.
There's so many possibilities. So
yes. Hello. Yes. Yeah. Professor, thank you very much for the talk. I have a kind of hypothetical question, which is, if there were no technological boundaries, but you had to choose, because I looked at those sensitivities of the seismic sensors, and they were quite narrow. So if you had to choose for a very so much more sensitive narrow, or same sensitivity but broadband detectors for future lunar missions? What would it be?
Well, I think it depends on what you're looking for. And it just so happened that shallow moonquake, deep moonquakes, signals at around half hertz or so, which is very close to the peak of long-band instrument in peak mode. We're just lucky that it happened to be. But if you're designing an instrument, I don't think we would start with that assumption. And I think if you can make it broadband enough, you should be able, and sensitive enough, you should be able to detect it anyway. So I would rather prefer to have broadband instrument, very broadband instrument, rather than try to specify any specific sensitivity at any given frequency.
Thank you very much.
Hi, Yosio. This is Nakamura. Thank you very much for the great summary. And I would like to also thank you for the almost a half century of effort. We are literally standing on your shoulder. And I would like to thank all the effort you have done. So my question is that, so you pointed out that to use the Apollo station as a network, synchronization of the time was pretty key aspect. And very likely in near future, we will have seismic station, but it will very likely be different missions, even different countries, different space agency. And if we want to use this as a seismic network, okay, time synchronization might be one key part. Do you have any other suggestions that for this future network that you ring a bell to us?
Well, I'm not in a position to give any suggestions how to do that. But I think it's to make sure that you have very, very high between station timing accuracy. How do you do that? Depending on, I think, what you people can do. And I don't have any suggestion except see if you can try to get the high timing accuracy, relative timing accuracy, then as we did on Apollo, because we were just fortunate that it happened to be that way. We did not plan to do that. And we could do that because when we took the data, looked at the data, oh, this is probably what we can do. And we tried that and it worked. And this is one of the very, very interesting, fortunate things. You do something without expecting anything. When you look at the data and something is there, and then you can just do it from there, go from there.
Okay, thank you very much.
I've also had a question. Did you have a way to remotely level the platform of the seismometer, or was that done only once at the beginning? So because now Mars Insight and so on, they had a leveling system. But did you have a remote way to do that as well for the Apollo stations, or not?
I think, you see, I'm not involved in designing the instrument, but I believe you can command to do the leveling at any time. I have to look at the command sequence, which is what command available, but I believe there was, you could level the instrument if necessary at any time.
Okay, I see. Thanks. You have a mic? Okay, there's another question.
Mm-hmm.
Well, thank you so much for your talk and for your work. So I had a question about the meteoroid impacts because you mentioned that there were several stations that were able to measure precisely the location of the meteors. Therefore, I suppose it was possible to measure how the meteor impact depends on the distance from the sensor. And therefore, I wonder if there were any studies that were trying to reconstruct the masses and velocities of those impacts based on seismic signal.
Yes, I think, let's see. Jürgen Oberst did look at those meteor impacts and estimating where they're from. And so yes, that depending on when they occur and how they occur, you can determine which way it's coming from. I think that's possible.
Thank you so much.
Is that the question you are asking?
It was exactly the question I was asking. I think when I look up that paper, I'll find the rest of citing paper, so that we probably perfect.
Any other questions? Yes, is there a question?
My question pertains to the regolith and its frequency response. Do you think the kind of sandy or soft nature of the regolith limited your high frequency response, or was it the instrument itself which had poor response at high frequencies?
That's hard to answer. The regolith, I think it depends. It's how the regolith reacts to seismic waves and how they also it depends on the frequency, but how the signals are reflected or transmitted through regolith is something. I think you need to look at some formulate regolith in some way and how the wave will travel through it, or reflected or scattered. And so it's a little bit complicated. I think it's not. I don't have a single answer to that question. I think it's something you need to look into.
Yes, another question.
Thanks for the nice presentation. So you talked about this shallow and deep moonquakes. You said that we don't know quite sure where the shallow, deep, the moonquake comes from. But what sets the scale? For example, the deep moonquakes, they have low frequency content. What sets the frequency content for the deep moonquakes? What sets the frequency scale for that?
Well, deep moonquakes and shallow moonquakes has clearly different frequency, and deep moonquakes happens at just above the interface between lower part of the mantle, which is high attenuation, which is either partially molten or even contains some liquid, and the upper mantle, which is a very high Q, which is low attenuation, and what sort of stress strain you can maintain at that conditions determines what sort of frequencies deep moonquakes have. And I think you have to go in more details how they occur. And shallow moonquakes are clearly different, much higher frequencies than deep moonquakes. And this is something we need to find out why it's shallow moonquakes such a high frequencies. And this may be related to how shallow moonquakes really occur, because we don't really know what is causing those shallow moonquakes. And there's many speculations about, you can make speculations, and shallow moonquakes are caused by some particles coming from outer space, and you can't really prove it. It's some indication that it could be, but this is one of the things when you set up more seismic stations and find out. That's one way, but other way is you can think all kinds of things about that, which even with available data. That's another way. I can't answer that question. So
Thank you. So I think maybe we can stop here. Thank you very much, Professor Nakamura, for your patience and answering all of our questions and for the great presentation. It was really an honor. And so let's thank Yosio again for the presentation.
thank you very much.